like to invite on stage now a colleague of mine, Sir David. And this is David Chisnall. He's the Director of Systems Architecture at SCI Semiconductor. He's a co-maintainer, along with Ben Laurie, Google, and Yukong Tao, Microsoft, of the CHERI platform. David's very knowledgeable. I've had a chance to interact with him, so I'm looking forward to this talk. Thanks, David.
Wow, it's very bright up here. So probably for this audience, I don't need to say security for connected devices matters. But what I want to talk about is how, by doing hardware-software co-design, we've got to a point where I think we can actually deliver that for things that are connected to systems that actually matter and where we have very long deployment lifetimes. So if I were to ask what are the most important things in computer security, I might get a variety of answers, but as Charlie hinted this morning, if you don't have memory safety, most of the rest of those don't matter. I want to spend just a few minutes talking about why that is. So when we talk about memory safety, what we're often talking about is its absence, the kinds of things that can go wrong if you don't have that property of memory safety. And this typically manifests in one of two ways. The first, which we either refer to as spatial or as bound safety, is this property that you can create an object, and in C, when you call malloc or you take the address of a stack allocation, you get a pointer to that object. And then you do some arithmetic, and in C, array indexing is just pointer arithmetic with some syntactic sugar around it. And that arithmetic takes you out of bounds of that object. And so now that pointer isn't pointing to the object you thought it was. It's pointing somewhere else. And C says this is undefined behavior. And if you write to that value, now you've corrupted some other object. And if you read from that value, now you've got a totally unpredictable value that came from some other place in your program. The other kind of memory safety problem is temporal, and we sometimes now refer to these as lifetime safety issues. And this starts in the same sort of way. You have a pointer and it refers to some object, but then you free the object, and that might be an explicit call to free, it might be a stack object going out of scope. And now you still have a pointer, but instead of pointing to that object, it points to where that object used to be. And you might still be able to write to that location and it have no impact on your program because that memory isn't being used. But at some point later, you'll find there's a new object in that space. And that new object is totally unrelated to what you thought it was. It's coming from a different bit of code. Nothing in this source code refers to that other object. And that's why memory safety bugs are so pernicious, because for most other categories of bug that lead to a security problem, you can read the source code, and once you know what the bug is, you know what the impact is. If you've omitted a check for some access control list, for example, reading the code that omits that check, once you know that that check should be there, means you can reason about it. You can say, oh, well, now someone can access this thing that they shouldn't be allowed to access. But with a memory safety bug, the behavior is totally unpredictable. It can be corrupting some other object somewhere in your system. And it might be that 99 times in a row you run your program and that impact is benign. But the 100th time, because of changes to the memory layout, that impact is now catastrophic and the attacker has complete control over your device. And when we talk about the kinds of systems that have 1 billion deployments, if it takes an attacker 1,000 times to get a compromise in one device, well, okay, sure, now they only have 100 million devices the first time they try it. This is really not good. And the root cause of this is really that we lose information when we're compiling. In the C abstract machine, that out-of-bounds access is undefined behavior. The compiler can do whatever it wants with that. That use after free, that referring to an object after it no longer exists, is undefined behavior. But the way that compilers for conventional architectures work is they just say, well, a pointer is lowered to an address. And from the hardware's perspective, it's just an integer. You do some arithmetic on it, and now you have another integer. And the fact that you use that to access memory, well, the compiler, the hardware doesn't know that this should be an integer associated with a specific object. It doesn't know that that object has been deallocated, and now actually no use of this pointer should be allowed. It's just an integer. And Simon described a lot this morning about how CHERI addresses that, and I'll come back to that in a few minutes. But I just want to highlight a few examples of why that really matters. We've talked a little bit about why it matters at the abstract, but concretely, some of you who were in Simon's talk this morning may recognize some of these slides. Heartbleed is one of the vulnerabilities that I remember particularly keenly because it came out a couple of months after I joined the CHERI project. But it's a really interesting example because this was purely an information disclosure bug. And usually we treat those as less severe than the kind that lead to memory corruption. And Heartbleed, as the XKCD comic says, was a problem in the DTLS protocol, so the UDP variant of TLS, as implemented by OpenSSL. And this has a heartbeat mechanism. Heartbeat also was one of the first vulnerabilities to get a snazzy logo, which is possibly why many people remember it. And so the client will send a string that they make up to the server, and the server will reply with that same string. And this can be arbitrary so that you can avoid cases where you get the same packet back twice due to retransmissions and you think the reply was from a later heartbeat. So you send a message, you ask for a reply with the length in it, but that length is just there for convenience. It's just so that the framing environment doesn't need to know that the data is from here to the end of the packet. But in the OpenSSL implementation, it didn't do that additional check to say, you've said you've sent me a 500-byte message. Do you have 500 bytes left in the packet? And if you don't, then I'm going to just drop this packet on the floor because it's clearly corrupted. And so if you sent it this request saying, please reply with hat, by the way, the word hat is 500 letters long, it would happily read off the end of that packet to whatever else was in memory afterwards. And unfortunately, it turns out, due to the way OpenSSL built their allocators, that was very often something from someone else's TLS session. But if you gave it a sufficiently large request, it would invariably be the server's private key. And that meant you could leak the private key of any server. And because that was possible, everyone had to assume that that had happened. And so every server ended up needing to roll over their certificates, generate new private keys, get new certificates signed. And so that simple failure to do a single bounds check led to hundreds of millions of dollars worth of work for people to do to address that potential. And that wasn't just a one-off. Heartbleed had a snazzy logo, so everyone remembers it. But when Google Project Zero did an analysis of Chromium, they found this kind of vulnerability accounts for about 70% of their critical vulnerabilities. When Microsoft did a similar analysis across all of their products over a 12-year period, they found actually the Google result wasn't unusual. The Google result was just, yep, that's the trend we've been seeing for all the time we've done this analysis. And you might think, well, these are big server workloads, big applications. Surely IoT doesn't have those problems. It makes far less use of dynamic memory allocation. It's running much simpler systems. But actually, that's really not the case. And this vulnerability in the network stack for ThreadX allowed, again, a single memory safety bug allowed an attacker on the internet to get arbitrary code execution. And even if you have an MPU, the network stack tends to be code that runs with high privilege. So this is game over for your device. But it's okay, because ThreadX is only used on 1 billion or so devices. So CHERI is a hardware capability system, and the 30-second summary is it teaches the hardware that pointers and integers are not the same thing. And on top of that, it can then enforce guarantees on pointers, so they can't be materialized from thin air. If you give the heap allocator a region of memory that it can use to allocate objects, it can then derive pointers to regions of that, but it can't just make up a new pointer and say, oh, hey, actually, this number I thought of that refers to some memory over there, that's now a pointer, go ahead. On top of that provenance property, it builds enforcement of bounds and permissions, and we also use the fact that pointers are detectable objects to build temporal safety mechanisms on top. And all of that's nice. You know, I'm not saying at any point fixing 70% of security vulnerabilities is a bad thing. We should definitely do that. But it's not the important thing. The important thing is if we have this as a property that we can rely on, then we can build far more secure systems by assuming memory safety from the ground up. I'll come back to that in a couple of minutes. But let's imagine you want to ship a device that has a long lifespan. And maybe you use Linux, because apparently all the cool kids are using Linux. Linux has long-term support releases, and they're supported for 5 years. I guess that's a while for a desktop operating system. It now has these community infrastructure partnership releases, and they're supported for 11. And now we're getting on to the kind of lifespan of a lot of consumer devices. But imagine you want to ship a device that you're supporting in production for 10 years. If you use one of those CIP releases, you can sell the device for 1 year, and then you either have to stop or you need to work out how you're going to move to a newer kernel release. And then CIP releases come out every few years, so now you have to move across multiple years of Linux kernel API changes for device driver interfaces and so on. So bringing your device drivers forwards, that's a huge chunk of work. And in a lot of the markets that we care about, you know, even things like smart meters, which you often don't think of as critical, have an expected lifespan of 15 to 20 years, and that is a scandal. You know, people are now saying that is not long enough for it to be commercially viable to be using smart meters. The absolute minimum should be 25. And that means you need to think about at least 3 iterations of something like a Linux CIP release. And this is starting to matter for device manufacturers because things like the EU CRA are making it explicit that they're liable for software vulnerabilities in the software that they ship. And it's not okay to just say, well, we got this from a third party, or we downloaded it from the internet and it's open source, it's not our problem. You have to be able to say, we will deliver security updates for this length of time. And if you're talking about critical national infrastructure, that for a length of time is not just, yeah, for the next 18 months until the next iPhone comes out. It's a decade or two. And that liability gets much larger the more complex the software you're talking about is. So this is a Linux CIP release that is halfway through its lifespan. And in the last 6 years since it was released, it's averaged 1 CVE per 2 days. So if you imagine you've put that in your device and you want to have someone triage those and say, well, maybe these ones are in device drivers that we don't ship. We don't need to care about those. That alone is basically 1 full-time engineer's job. Or you could go the other way and say, we won't triage them, we'll just always ship the fixes. And now you need to have a QA team that can do a complete turnaround every 2 days of a new version, ship those to customers, and have customers who are happy to deploy a new software update every 2 days. But often for low-end embedded stuff, you're not shipping Linux. And I feel like I've been unfair to Linux here. It's huge. But let's look at something smaller like Zephyr. the Zephyr release from about the same time has only averaged 1 CVE every month or so. And that's the kind of scale where you can imagine if upstream goes away entirely, well, you fork the version that you ship, you maintain security updates, maybe that's affordable. And that improvement is a function of the scale. Right? The Linux kernel these days is 40 million lines of code. Zephyr is 3 orders of magnitude smaller. But if you start from assuming a memory-safe substrate and you build something on top of that from scratch, you can get another 2 orders of magnitude smaller. In CHERI at RTOS, we don't have anything that is omnipotent like a kernel, but our closest equivalent is 350 instructions, and typically each of those lines of code in Zephyr or Linux compiles to multiple instructions. But even assuming 1 instruction, 1 line of code, we're still 2 orders of magnitude smaller. And this fundamental building block that we have with something like CHERI means that we can privilege separate even the things that in a microkernel would be aggregated. You know, we do all the microkernel things of saying, well, network stacks and message queues and file systems and whatever, they're all isolated, and maybe they're isolated into multiple compartments. But we also isolate the core operating system functionality. So we have a loader. That starts when the system boots, so it has the capabilities that grant access to all memory. But it's not part of your attack surface. It runs at system boot and then erases itself. We have the switcher that I mentioned on the previous slide. This is the only thing that holds the rights that would allow you to do the equivalent of breaking process isolation on a conventional kernel or microkernel. And that's 350 instructions, and we're working with some folks at Google and Oxford on formally verifying that. We have a scheduler, and the scheduler has to be trusted for availability. It chooses which thread runs next, but it's not trusted for confidentiality or integrity. So even if you get arbitrary code execution in the scheduler, you don't get to see what a thread is doing or what a compartment is doing. You just get to choose which thread is running. And then finally, we have a heap allocator, and this is optional, but if you want to be able to dynamically allocate memory, I said previously the hardware enforces spatial and temporal memory safety, but the hardware doesn't know what an object is unless something tells it. It provides the mechanism, but you still need to provide policy from software, and that's what the heap allocator does. So let's imagine you're shipping a new product, and you want to be able to display a QR code for initial configuration or for pairing with a mobile app. And typically, until recently, the way you'd have done that is you'd go to GitHub and you'd search for QR code library and you'd pick the top one. And now maybe some people would use industrial scale plagiarism machines to generate an incredibly buggy QR code library instead. But the same problems apply, and these are really 2 categories of problem. One is it just might not work. But fortunately, we know how to mitigate that risk. We have testing. We can generate a load of data that looks like the things we want to display in our QR codes. We send them to the library and we check that does the thing we get back work as a QR code for that data. And then we have a reasonable amount of confidence that, yeah, this actually is a valid QR code library. But if we think about supply chain attacks, whether they're on the LLM you're using to generate this library or nation-state adversaries who want to compromise your device, who put some backdoor into your code, or even just accidental bugs because, hey, software is complicated and not everyone gets it 100% right. All of these are things that are very difficult to prove. Proving that any piece of software contains no security vulnerabilities is, an unsolved problem in computer science. And this is really what we designed both the CHERI at ABI and compartmentalization model, but also the higher level auditing tooling that's built on top of that around. This idea that we want to be able to reason about what rights any piece of code has. So we can take that QR code library and we can put it in a compartment. And compartments are very lightweight. If you go out to our booth upstairs, we have a couple of demos that have 10, 15 compartments running in 200 to 300K of RAM. So these are not heavyweight things like an OS process. We can reason about what devices does it touch, what functionality does it expose for other compartments, what functionality does it import. And when you expose functionality from other compartments, that can then be mediated by a software capability model. So you may be able to allocate memory, but only when you hand the allocator a software capability that encapsulates your quota. And so we can reason about, well, this compartment can't allocate more than 2K of heap memory, or this one can ask the network stack to connect to a server, but only this domain on this port with TCP. And so this really lets us reason about what the worst can be, what's the worst that can happen if the code that you've taken from a third party or from that junior engineer you just hired or from whatever source, what is the worst impact that that can have? And that some of that is enforced in the source code level. You can think about what rights am I explicitly giving it in terms of pointers I pass to it. But a lot of security properties are really about negatives. It's about saying this component shouldn't be allowed to do any of these things. And so you can have a policy that says this thing can't call any other compartments, it can't talk to any devices. And so we can, at the source code level, just treat it as a pure function. And so this is the thing that really lets us enable fearless code reuse. Not only do we have that tiny TCB that means updates can be infrequent, we don't just try and protect the foundational operating system code. We're not saying we have a secure system that you can now layer many insecure things on top of. We've built a platform that enables other people, and actually looking around some people in this room, to build things that really respect the principle of least privilege. And we will be shipping chips next year. Everything I've talked about today is open source, jointly maintained by SCI and a couple of startups from the US West Coast that you might have heard of. So, thank you.